I'm going to present today on score-based explanation for classification results. I will go to different results that we have obtained with co-authors that I will mention along the way. At the end of my slides, I have a list of references, so I'm not going to be citing much during the presentation. And I can share the slides with you if you are interested at some point later on. Okay, so I am a professor of the University Adolfo Ibañez in Chile, and also a member of the Millenium Institute of Foundations of Data Research on Data in Chile. I have been working on explanations in both in databases and in machine learning for some time in the last few years. So let me start with a very simple examples in the context of databases. Yeah, so it's a very simple one to start. Introducing the subject, the idea of scores. So we have a table containing official stores, a table containing a receiving relationship between stores, and then we are querying. What are are there pairs of official stores? That belong here in a receiving relationship over here. Yeah. And it is easy to see that the query can be expressed in this way, of course, and it is true in the database because it is possible to create the appropriate joins that is expressed here because the store has to be official. So that is true. So the question is, what tuple cause the query to be true? Yeah. Of course, it's a very simple database, but it could be a very large one, and this could be less obvious, maybe. Yeah. And the related question is, how strong are they as causes if we manage to identify them? Yeah. For example, we would expect tuples receive S3, S3, the one over here, and receive S4, S3 to be causes because they participate in the satisfaction of the query because it is possible to create joins with this table over here. Yeah. So, so in this case, we are looking for explanations for a query result, right? Excuse me, I'm a bit congested. Another scenario, we have a bank owns a classifier that we can consider as a black box. We don't know how it works. And then there comes a client of the bank and requests a loan. This is an entity, and then the answer is no. And then the client requests a loan that is rejected. For example, could be a record of feature values, yeah, for name, age, income, etc. The question is which are the feature values? Excuse me, I'm very congested. Which are the feature values that are most relevant for the classification outcome? That means for the label known that we are obtaining here. And then what is the contribution of the feature value to the outcome? Yeah. So the most relevant feature, what is the contribution of each particular one to the outcome? So these are natural questions we want to identify. So these questions are at the very core of explainable AI. Yeah. You will have to excuse me, but I'm really congested. So I get this kind of allergy this time of the year. Okay, one possible approach comes from causality. It has been developed in AI for 3 decades or so, and in particular in the field of actual causality. Yeah. It also provides, actual causality, the notion of responsibility. It is a measure of causal contribution. Yeah. And this idea of actual causality and responsibility, they are based on counterfactual interventions. Yeah. So they are basically hypothetical changes of values in a causal model to detect other changes. Yeah. You change something here and there, hypothetically, possibly, and then you see what happens with other variables. And in this way, you kind of start trying to identify actual causes. Yeah. This is very well formalized by not going into the details. For example, what intervention could we be talking about? Do deletions of certain database tuples make the query false? Yeah. Or do changes of feature values make the label change to yes? Yeah, to change the value. Yeah. So we have investigated causality and responsibility in data management and classification. So counterfactual explanations have a role to play in both of them and other areas. Yeah. We have investigated the semantics, for example, what is the integration of these notions with the integrity constraints, for example, or domain constraints, computational mechanism, intrinsic complexity, logic-based specifications in terms of answer program, for example, and reasoning about counterfactuals. Yeah? So we have been working on in that area. I'm not going to talk about all of those things. So for the gist, in relation to responsibility, here we have the original table, and then if this is the same query we had before, but if we delete these two tuples, the one over here and the one over here, then the query is not longer true in the database D prime that we obtain through those deletions. So this receive S3 turns out to be an actual cost, but deleting it alone will not invalidate the query. It needs some company. So this has to be deleted as well, together with this. So this becomes a minimum size contingency set for this tuple, for this to be an actual cost for the query. Yeah? So we have these contingency sets that are important. Yeah. So the responsibility of receives, this one, is defined as 1 over 1 plus the size of a minimum size contingency set that has to accompany the tuple in question. Yeah, in this case is 1/2. Whereas if we delete this tuple S3, we immediately invalidate the query. So the responsibility is 1 plus 1 plus 0 because we don't need a contingency set. So the value is 1 and we have a counterfactual cost. Yeah. So this is the idea. In the context classification, this is the entity that got the label no. And then if we change maybe the age to 25, we get the label yes. So we change the outcome in the same way as we invalidated the query here. Or if we change these two values together, we obtain the label yes. So in this case, the value for age would be a counterfactual cost with explanatory responsibility equal to 1. I'm not giving the definition for the moment, but following the same idea of 1, but income is an actual cost with responsibility 1/2 because we also need to change an additional feature value. Yeah. So, and after you get the explanation, you may say, well, maybe this action can, these causes can help us act, do something about us, about changing the outcome of the loan request. Well, so in this case, now we kind of start talking about actionable causes and non-actionable causes in the sense that some of them are feasible. For example, it might be feasible, well, to change the job to get 5K more and maybe change the neighborhood, but maybe waiting for, I don't know, 7 years, I mean, to get the loan is something that we are not willing to do. But okay, but that goes in a different direction, but it's interesting to see that things are investigated, right? No, not causes are equal in the sense of applications, right? So another approach is based on the Shapley value, and this I'm going to talk mostly about this. So database tuples and feature value can be seen as players in the coalition game. Yeah, so the feature values are players. Each of them contribute to a shared wealth function. Yeah, and the Shapley value is an established measure of contribution by players to the wealth function. It has been introduced in coalition game theory, so not directly for in databases or classification, but it can be applied in both settings. So actually, it is very nice. It emerges, I mean, this measure as the only measure that enjoys certain desired properties. So it follows a set of axioms, so to say. Yeah, but in order to apply it for each game, one has to define the appropriate wealth or gain function. Yeah, so we're going to see a couple of them. So in the case of the query, yeah, in the database, this is the query. Yeah, and the gain function could be just the value of the query. I mean, 1 or 0, a numerical value, depending on whether the query is true or false. Yeah, so the gain function is quite immediate in this case. So, and a set of tuples, because we have a database, but we consider a sub-instance, a set of tuples, make the query true or not, with some of them maybe contributing more than others to making it true. Yeah. So this is the Shapley value that we can use in this particular setting, where the query is the gain function, and this is basically what we are doing here. we are trying to quantify the contribution of tuple tau to the query result. This is the general Shapley value expression with the particular Shapley gain function that we are considering. And here, basically, we are considering all the possible permutation of sub-instances of D. So we have D, we leave aside the tuple we are analyzing, and then we consider all the possible sub-instances. And those sub-instances, the query will be true or we will false. And we consider the query, the difference between the query being true in this sub-instance plus the tuple in question here, and not having the tuple in the same sub-instance. So basically, here we are playing something like a counterfactual game again, the difference between having tau and not having tau, right? And then we consider all the possible permutations of these sub-instances, and this basically is associated to all the possible permutations, and then we compute the average of these differences. So this is the Shapley value they apply to this particular gain function. So this is basically an average of difference between having tau or not. Counterfactual is implicitly involved and unaggregated, is an aggregation here. And we have investigated algorithmic complexity approximation problems with Esther Lifshitz, and Benny Kimefer and Moshe Sebag. Esther is here with us, I think. So we did some work on this that we published in the ICDT paper. So, and we also extended, the results, to aggregate queries. This is a very fully detailed analysis of the Shapley value as a measure of contribution of tuple to a query result. Actually, Esther with co-author has extended this measure as a measure of contribution of tuples to inconsistency of databases. And actually, it's interesting to just mention, passing by, that in all these areas, there are some underlying and useful connections to database repairs with respect to integrity constraints. In our research, we have strongly relied on those connections to obtain results, for example, for responsibility. So I'm not going to say much about that, but it's a message I want to convey. And there are a couple of references at the end. Yeah. Now the score-based approach. For classification. So we're going to assume, to simplify things, that the classifier is binary. So we have the labels 0 and 1. They have a set of players F. In this case, they are the features. Everything is going to be relative to a particular entity, the one that we were classifying, the guy who was requesting the loan. Okay. So everything is relative to that one. So we have a set of features, and then the gain function now is different. We consider this gain function. We take a subset of players S, in the same way as we had a sub-instance of the original database. Now we have a set of features, right? It's a gain function associated to E, as I said, and it is the expected value of the labels that we obtain over entities that differ from the given one, or possibly differ from the given one in all the features that do not belong to this particular S. That means we fix a set of features, we leave those values fixed, and we possibly change all the values for the other features outside S. Yeah. So we are going to get many different possible versions of E that coincide with E in S, but possibly not in the other, for the other features, right? And then we classify the resulting entities and we compute the expected average, the expected value. Now, this is going to be an average of the labels, basically. So this is not our invention. Actually, this has been a popular measure, a score in machine learning for the last few years. It is a Shap score. So basically, the Shap, we are computing here the Shap score of a feature F, particular feature F, given this gain function associated to the entity at hand with respect to the full set of features in the record, of entities. So basically, all I have to do is change the definition I had before, replacing the gain function I had before by this new one, that is one over here. So we get this expression that looks horrible, but is exactly the same we had before. All the possible permutations here. And then here we have the difference between having f, the value for e fixed, and not having the value for e fixed here. So here, basically, f is left outside S, yeah, and we consider all the entities that coincide with the original entity in the features in S, and here we add the condition that they have to also coincide on the feature f that we are analyzing here, yeah. So, and then we basically compute the difference of expected value. So again, there is a counterfactual game here. Yeah. So this Shap score has become quite popular. It was introduced by Lee and Lundberg in 2017, and there are many papers about it. Yeah? So we have to assume, of course, the probability distribution on the entity population on the entities, right here, the population of entities, and that might change these values, of course. Yeah? In the same way, actually, the explanatory responsibility score that I briefly suggested before can be generalized as expected value for multi-valued features, as I will show if I have enough time to do that. Yeah. What is important to notice is that both RESP and Shap, or XRESP, RESP, and Shap may end up considering exponentially many combinations. We are considering all the possible subsets of f minus f, all the possible sub-instances of the original database. So this is, by definition, exponential, right? So the question is as to whether we can compute this efficiently, right? At least in some cases. Yeah, but it is by nature exponential. And actually, there are cases that are proved to be hard. Yeah. And in a paper as I said, the reference at the end, we have experimentally compared RESP and Shap, and actually it's very interesting that they give very close results. Yeah. Okay. The question is, as I said, this is intrinsically complex, or by definition complex. Can we do better when we have the classification model? So instead of having a black box, now we have a classification tree, for example, something like this. Yeah. Would it be possible to compute the Shapley value or the Shap value more efficiently? So what do we have, a decision tree or a random forest or Boolean circuit, for example? Yeah. Can we compute Shap in polynomial time? That is the question. Yeah. And we investigated this problem in detail in a RelationalAI 21 paper with Marcelo Arenas, Pablo Barceló, and Miquel Monet. And we gave a positive answer for decision trees, random forests, and some classes of Boolean circuit that include decision trees, for example. Yeah. So, but that it was an open problem. I mean, the conjecture was it was possible to do that in polynomial time, but there was no real detailed proof of that. So in some cases, the computation is tractable, and in other cases it's intractable. Yeah, provably intractable. So for the tractable cases, we provide algorithms, and in particular, we get the tractability result for decision trees and random forests. Yeah. We also investigate the approximation algorithm. Actually, they don't appear in RelationalAI in this paper, but in the journal version that we have submitted. But I'm not going to talk about the approximation. So there are many interesting problems to investigate. Before going into details of what I am telling you about here, I mean, let me give some final remarks. Well, not final remarks, intermediate remarks, so to say, to give a bigger picture. So there are many interesting open problems to investigate. For example, adding semantic or domain knowledge being an important one. I mean, because we may have domain knowledge that is not considered when we compute the responsibility score, the Shap score, and we would like to bring that knowledge into the picture. So it is also important to be able to reason about counterfactuals. It is interesting to see what are the connections between this kind of explanations with model-based diagnosis as proposed in AI and KR some decades ago by now. The explanations are also at the base of fairness and bias analysis. So identifying unexpected or undesirable high score features becomes irrelevant. Yeah. Another promising problem has to do with high order analytics on explanation. If we collect many explanations, well, we have a new set of data, so to say, from which we might want to learn something. So what else can we learn with T here about the population or our classification mechanism by analyzing our explanation? Well, all these are things that we are investigating in our ongoing research and future research. But these are, I'm not going to say much about this. Let me give you how much time I have. Okay, I'm going to say very little about this. Let me give you the gist of the responsibility score. So in this case, we have this work that we did with Dansuchu, Hula Agina, and Max Schleich. And then we have what is the idea here? We are considering the label of the entity minus the expected value of the labels for entities that coincide in all the features but F, the one at hand, the one for which we want to obtain a score. It is very easy to compute and gives reasonable results. Actually, it is very close to the results of more sophisticated scores, and it's very easy to compute. And of course, it requires an underlying probability space. Yeah, and there is no need to access the internals of the classification models because all we need is the classifier represented by L. Yeah, but the point is that changing only one value, the value for F, may not switch the label, so no explanations are obtained. So what we do is we extend the score by bringing into the picture contingency set of feature values, yeah, as I suggested a few slides ago. And this is the rest score that we have defined in detail in this paper. And where we start with what is the idea? Basically, very simple here. We have, as I said before, a value X. We want to expect this value for this feature. We get the label 1. We want to change the label to 0. Then we change X to X prime. It's still 1. It doesn't change. Well, then we leave the same value here, and we start changing other values, and then we still get 1. But suddenly a situation like this occurs. Yeah, we have changed X into X prime, and these values Z and Y into Z prime and Y prime, and we get 0. So we can say that this X is the X here is an actual cause for the result 1, and this set Y associated to this is a contingency set for X. Yeah, for this X. Yeah, this is the idea. So basically, I don't think we need to go through the details. Basically, Y is a minimum. If Y is a minimum size, I mean this contingency set. Basically, the responsibility will be 1 plus 1 minus plus the size of this minimum size contingency set. That is the idea. However, I want to skip this. It's an example, but I will leave you to. So, sorry, let me. Yeah, but actually, there might be, of course, many situations, I mean, that may occur in terms of the sizes of this contingency set and the values that we obtain. So it could be the case, for example, that there is only one value X prime that allows us to change the label, and many others alternative values for X that do not change the label. So having just one value that changes the label may be too little in comparison to the large amount of number of all other values that do not change the label. So in this sense, it is more natural to extend this idea that is already here to an average, considering all the possible values that we can make X take. Yeah. So this is the generalized version of the rest score. Basically, what we have is it is basically, I don't think I'm going to go through all the details, but basically what we have to do is we change W, a record W of features, right? Yeah, they are different from those that the original entity is taking. Yeah, these are, think of the X prime. So we are changing now a set of features, right? And then we set, these are the values that are going to be the elements of the values in a contingency set. So we have now E prime that is obtained by giving to the values in E, the values in W bar, the values in the contingency set. Yeah. and then we still have the same label with the change. So we may need an extra change. So we pick a value from the domain of F star, the one that we are assessing, to which we are going to give a score. And then we give this value to F star, the one we are analyzing. And then it happens that we do change the label. Now we get, instead of 1, we get 0. So we can say that F star E is an actual causal explanation for LA equal 1 for that label, with the contingency set gamma, the one we started from here, changing the values for those features in gamma. Yeah, but now we basically change all the possible values for E, for X, sorry, with this fixed gamma. Yeah? So the responsibility now, depending on W, it depends on W and gamma, is going to be basically the same I had before. The difference between the label for E prime, yeah, that is one over here, minus this expected value that I considered before, over 1 plus the contingency set of gamma. And now we took an arbitrary good gamma as contingency set, and now basically we have to maximize this responsibility with respect to gamma and W. So that means that consider all the possible combinations, and we get now a responsibility score that depends only on the entity at hand and the feature value to which we want to give a score. Yeah. So this responsibility score basically it seems follow the same idea of counterfactuals of a counterfactual game. Yeah. So this is a I'm going to skip here how we perform the experiments. So I'm going to leave this with you. And let me talk about this, what I promised. So this is, again, now we are talking about the Shap score and its properties. So we have here this expression for the Shap score, as before, haven't changed anything. And now we want to analyze how difficult it is to compute this. So this it depends on the entity and depends on a classifier L that we can access as a black box in principle. But now we are assuming we are going to have our classifier on display accessible. Yeah. So the domain is everything is going to be binary here. So the entities are elements of this set, sequences of zeros and one of length n. That is a number of features. There is an underlying probability distribution that I'm not going to mention for the moment. And then we consider these two problems. We will identify the Boolean classifier L, yeah, with L. I mean, that is the classifier. So SAT L is a set of all the entities that get the value 1. Yeah, all the entities in this space that get the value 1, that are classified with 1. And sharp SAT of L is basically the number of satisfying assignments or satisfying entities, those that get the cardinality of the set of entities that get the value 1. Yeah. So this is counting the number of inputs that get value 1. The proposition, and all these propositions are lengthy computations. I mean, that can be found in the paper and even more in the extended version. I'm not going to do much except for the one that is crucial. So for the uniform distribution on this space, we get that sharp SAT L takes this expression. What does it mean? Basically, that if I am able to compute sharp efficiently, then I will be able to compute sharp SAT L efficiently as well. And we have a Turing polynomial time reduction, right? In this case, I'm not particularly interested in the details here, but basically we have calls to Shap in order to compute this. Yeah. So this is what we have: a reduction in polynomial time according to Turing, the Turing reduction to Shap, because it is one to many, because we have several calls here, right, to Shap. Yeah. So when this is hard on the left-hand side for a Boolean classifier L, computing Shap is also hard, obviously, right? So negative corollary, computing Shap is sharply hard, difficult for circuits for which this is hard, right? So this is linear perception classifier that is obtained by a reduction for knapsack Boolean classifier defined by monotone to DNF or monotones to CNF classifiers. So are there other classes of circuits, right, for which this can be done more efficiently? Other class of Boolean circuit classifiers? That is the question that we wanted to investigate. Okay, so, and we concentrated on this class of circuits, DD Boolean circuits. I'm going to briefly describe. So a Boolean circuit over a set of variables is in this case, is directly a cyclic graph. Boolean circuits in general, we have basically, let me, it's easy with the picture. So each node without incoming edges, right? Basically, you see over here, right, are labeled with variables or values from 0 or 1. The one over here, right? Each other node is labeled with a gate is a negation or conjunction or disjunction. There is a single sync node from which we read the classification, right? The label, the output. And then an entity is accepted by a classifier when we get the value 1, assigning values to these variables according to E. Yeah. And then we can talk about the induced subgraphs. If we have a gate G, like this one over here, C of G is an induced subgraph containing gates on the path in C to G. Yeah, basically it is going to be this lower portion over here. The variables of G is a set of variables of this lower part here. These are the variables in this case, x2, x3, x4, right? It's a useful notation that I'm trying to keep to a minimum. Now, a circuit is deterministic if every OR gate, like one we have here, with input gates G1 and G2, this is G1 in this case, X2, and this is G2, then the values for this one and this one are different for every possible E. It is very easy to see in this example that for every possible entity, the X2 and the AND here always take a different value. Yeah, I'm not going to go into that. So this is a Boolean circuit that is deterministic. Yeah. So basically, what this is saying is this OR acts as an exclusive OR. Yeah, that is a reading. And now C is decomposable if every AND gate, the one over here, for example, with input gate G1 and G2, we have that the intersection of the set of associated variables, right? This is G1, this is G2. The variables here are this, the variable here is X1. So they have empty intersection of set of variables. Yeah. So we will consider C, the classifier, to be deterministic and decomposable circuit. So this is what we call the DD circuit. Yeah. Everything is going to be based on those circuits. And why are they interesting? Well, several classes of Boolean models can be translated in polynomial time into DD Boolean circuits, decision trees, order binary decision diagrams that are also quite popular in these days for some reasons. Another that I'm not going to mention, but these two are particularly relevant for us. This is where the problem started from, and there are interesting applications lately of these circuits over here. So I'm not going to say much about, but for example, why decision trees are decision trees can be compiled into this class of circuits. Basically, there is a way of compiling this decision tree. This decision tree, yes, 1 0 1 0 1 0, right? You can take this and produce a circuit, and it turns out that the circuit is DD. Yeah, there is a mechanism, inductive mechanism for doing this construction. Basically, this is the proof of the constructive translation. Yeah, I'm not going to details, but I'm going to leave the slides with you. You're interested in seeing the details, right? So what is the final equivalent circuit? I mean, associated to the decision tree is basically the compilation of that we obtain inductively of the top node over here. Yeah, that is a resultant circuit. Yeah, this is computable in linear time. So for these cases, Shap computation in polynomial time is not precluded. It could be the case that Shap could be computed in polynomial time, yeah, because it's not excluded by the results that we had before, possibility results that I mentioned somewhere before here, yeah. So it could be the case that we can do a better job. So, and we can, right? So the proposition that we have is that for this kind of circuits, sharp sat C can be computed in polynomial time. And the idea is just a bottom-up procedure that inductively compute this sharp sat for the subgraph, induced subgraph for each gate. And then you keep going and then you construct this for the full circuit. So to show that, so that means it is possible that we can do better with the classification trees, for example, right? Or these circuits in general. So to show that Shap can be computed efficiently for these circuits, we needed more detailed analysis. This is just showing that in principle it is possible. So we're going to assume the uniform distribution for the moment, and then we create a related problem. That is what I call the satisfiable circle of an entity. What is this? Basically, it is set here. It depends on E, notice. And this L is a number of features. Yeah. What do we have here? These are the satisfiable circuits. I'm sorry, the satisfiable entities. Yeah, those that get the value 1. But we are also interested in those that do not go too far away from the original entity E. So this is captured by this. So here we have the set of all the alternatives entities such that they, in norm 1, they differ from the given entity by L. I mean, that means E and E prime differ exactly in L value feature values. This is the L norm. L1 norm is the sum of the absolute values of the difference between the two entities component-wise. So basically, we are differing only in L feature values between E and E prime. So, and then we also ask from E prime to be satisfiable, to get the value 1. Yeah. And sharp sat of this thing is just the cardinality of this set of entities. Yeah. And this is closer will be closer to Shap. Actually, one can prove that if we can compute this sharp sat in polynomial time, it is also possible to compute the Shap value that we are looking for this particular value in an entity E, yeah, with the associated gain function. So basically, now the problem is how to do this, right? And at this point is where we are going to take into account the D, lowercase d and capital D, because we haven't used it at all. So the main result here is basically, actually, it's very easy to, well, it is full of details, I mean, calculations, but the idea is not difficult. I mean, main result, this can be solved in polynomial time for DD circuits, entities E and any value between 1 and the number of features. Yeah. And the idea is just inductively compute these things. I mean, for the subgraph, right? We go inductively through the subgraph, right? For each gate G in the circuits, an integer value L equal or less than the number of variables in the gate here. Yeah. So the input gate is a simple base case, basically, and then not gate, what you do, have C for not G, that means a subgraph graph below a negated gate, then basically it can be reduced to the same thing without the negation. So it's a typical inductive construction. It is a bit complicated expression, but it works. And now for the OR gate, now we use determinism, yeah, and then we have basically for a gate that is the union of two gates, is basically we can compute it through the sum of the sharp sats of each of the two components. And for this, determinism is crucial because determinism is treating every OR gate as an exclusive OR. Yeah. And for the conjunction, it uses decomposition. Yeah, there was a property associated to the conjunction. And then we have basically obtained the product of the two components here. So we get rid of the n, and now we have G1 and G2. So basically, this is the main result. Well, it's a lengthy computation. I mean, all the computations here are rather long, and but they work. So the theorem is that Shap can be computed in polynomial time for this kind of 6 circuits under the uniform distribution. Yeah. So every entity every combination of zeros of 1 is equally likely as any other. And the corollary then is Shap can be computed in polynomial time for decision trees and random forests and OBDDs, etc., under the uniform distribution, which is good news, right? Actually, it can be extended to any product distribution, yeah, on the space of features, yeah, of entities, sorry. The uniform case is a particular case with the probability equal 1/2 for each value. So it can be extended, and we do that in the paper. So this is, and actually, all this has been done with binary features. For beyond binary features, well, we could do binarization features. I mean, we have something like this, for example, where the feature is a decision tree, but features are not binary. And we have, for example, here 3 feature values. Well, we can binarize, I mean, these introducing propositional features for every possible value, basically, and we can transform this into a binary decision tree. So this can be extended to these cases as well. So of course, there will be some combinations that are not possible, but this is another thing. For example, it is not possible that all these features take simultaneously the same value, or these 2 take simultaneously the value yes and yes, or 1 and 1. Yeah. So actually, by the way, that has to do with this idea that I mentioned before of introducing some sort of domain knowledge or semantics into these definitions and computations. Yeah. That is interesting to explore. So our polynomial time algorithm for Shap can be applied to ordered binary decision diagrams, as I mentioned before. And they are particularly relevant for several reasons in knowledge compilation. In particular, I mean, to represent opaque classifiers in this form. For example, binary neural networks. There is interesting work by Darvish and co-authors, I mean, in this direction. So if we represent the neural network as an OBDD, well, we can start applying Shap, right, to those alternative representations. So I think that is interesting. So that's why I said before it is relevant for what is going on in these days. Yeah. So this is just to basically, this is where I am ending. I mean, this is a OBDD. Basically, it's a generalization of a decision tree where basically, well, we don't have a tree anymore. We might have a graph. But still, these are decision edges, I mean, 0 and 1. And actually, it could be possible to transform this OBDD into a decision tree following a procedure that is not unlike the one that I showed before for decision trees. So, I mean, OBDDs can be translated, that is what I'm saying, as DD circuits, more or less in the same way as we transform this one into a DD circuit. Yeah, the order means basically that in all the paths here, the variables have the same order. Yeah, that is a restriction. Yeah. So basically, this is what I wanted to present. There are many things to explore. Haven't mentioned anything about approximation results that we do have in the paper with Esther, Lipschitz, and Benny Kimmerfeld for queries that we also have for Shap, but well, at some point one has to stop. I hope to have given a picture of what's going on. These are some references that are related to what I mentioned today. Yeah. So, and well, I'm open for any comments, questions, or I hope I can answer them.
Thank you. So I see there's clapping on the participant list. I see there's a question from Jorge. You want to unmute?
Yes, Jorge.
Jorge, sorry.
No, that's fine. So first of all, thank you for the interesting talk. Very informative. I guess that more than specific questions on the methods and the specific details, I have more like a meta question. Try to catch something from your experience. Since the methods that you have described aim to provide explanations, right? So how do you perform this really and always hard task of evaluating and try to understand or how to basically, how do you tackle this approach and evaluating on an explanation? Does it make sense to a user? So how do you tackle this? Because I think it's always hard, right? Especially when we're talking about explanations.
I'm not sure I understand. You mean you are talking about the actual computation of the Shap values, for example?
No. For instance, because the Shap value will provide some sort of insight on the model, right? Like these features are more important or less important, right?
Yeah, okay, of course. For a particular entity, input entity, these are local explanations. Maybe I should have explained that. They are not saying much about the whole model. They're talking about the combination of the model and a particular input. Yeah. So these are local explanations. And that's why I mentioned before, it would be interesting to do something like a second order analytics here. If we had a bunch of explanations for different features, for different entities, what can we learn beyond that? And actually that, I don't know, is that what we're talking about? But let me mention that this is a problem that actually was posed to me by someone from industry. We are confronted to this problem. We are getting explanation now. What do we do with them, right?
Yeah, exactly.
Analyzing specific entities. Sorry. And actually, I realized that the problem was basically open. I haven't seen any work done in that direction. But all we get here is a bunch of, or one, or possibly many local explanations. And then they can be computed in polynomial time for certain class of circuits. And there are algorithms. Actually, in the extended version of the paper, we have a detailed algorithm for doing that. And in the work with the STER, for some class of queries, we have also concrete algorithms. Yeah. I don't know if I'm answering a bit of.
No, I mean, that definitely gives more context to the actual outcome of your work, like more concrete, right? Like you have a bunch of local explanations. It's more like a postdoc explanation, basically, right?
Yeah, exactly. Yeah, so that exactly, that's the point. And I think one should and one could go beyond that. I mean, that is my. And there are other methods that are global, right? That provide somehow an explanation for the whole model, right? Well,
yeah,
how do we
Bayes and rule lists and stuff like that.
Yeah.
Yeah.
So what would you? I mean, I think those are things that have to be explored. I mean, there is much room still for research here.
Yeah. No, thank you, but yeah.
Actually, this for a long time, people thought, I mean, that Shapley could be computed in polynomial time. I mean, but nobody gave a fully detailed, I mean, an acceptable proof of this. I mean, so we just gave a proof. So we have an algorithm that works in polynomial time. So this is quite recent, and so that is the beginning. Just to start computing things in some case. So we have to go beyond this, definitely. See, so I asked a student of mine to look into this second order analytics and explanation. But I think it's one of the problems, and many other problems.
Thank you. Thank you for the talk again.
Thanks, Jorge. Jorge, right? Who is?
Yeah, Jorge. Yeah.
Any more questions? Because I have one. It's a bit of a soft question. Can you do some pre-processing of the database in order to help you out, right? So you know, data sits there overnight, or someone is having like a mortgage meeting in 2 weeks. You want to prepare for when they show up, so you can do lots of queries very fast, right? Is there some kind of pre-processing you can do in the database in order to speed that up, so that kind of the online querying is going to be faster, right? Does this make sense? Sorry, I'm a bit of a high-level question.
I don't remember to have seen anything exactly like that. I think I saw Esther. I don't know. She may have seen something, but Esther, feel free to
I mean, maybe the question is completely,
No. I think your question is important, but I think I would rephrase in a different way. Actually, implicitly, I wouldn't. Let me. This has to do with. Sorry. Let me. I think that is relevant. Actually, this is very, very relevant. Actually, Gabriela, who is my student, who is attending the presentation, is looking into this issue now. So. Addition of semantic and domain knowledge being an important one. So, for example, that has to do with, is related to your question in some sense, right? I mean, you might want to say not consider certain entities, right, or tuples in a database for some reasons, right? My approach, the one that I have started to explore, is based on introducing constraints that are somehow compiled into the definitions and the computation, of course, of the scores. You know, John, we are not changing the gain function of Shap, but we may change the distribution, right? So basically, you get something like a conditional distribution. So that is related to what you're saying, but it's not that we are just basically deleting and modifying data a priori, right? Or possible counterfactuals a priori. Basically, we leave them, but possibly we give them low probability. Or